One moment. Can you see it now correctly?
Okay. The link and the other facilities for the online presentation seems to be okay. It is a really great pleasure for all of us to have here Professor Gomez Nicolas for the noticeable talk on induced structures on generalized geometry. Professor Gomez Nicolas, do welcome to your presentation, please.
Okay, perfect. First of all, I want to thank all the organizers for giving me the opportunity to talk here. I'm going to present a joint work with Fernando Tallo and Rafael Santamaria. First of all, I think I should define the generalized tangent bundle or big tangent bundle. And this vector bundle is defined as the Witnessium of the tangent and the cotangent bundle of a manifold. And it was introduced by Nigel Hitching in 2003 and later studied by Gualtieri in 2004. The rank of this vector bundle is 2 times the dimension of the manifold, and the section of this bundle can be seen as sums of vector fields and one forms. One question that may arise when we present this bundle is the following: why should we study it? Well, when it was presented, it could be seen that this bundle is related with the development of other science fields, such as string theory. And lately, it has been useful in order to construct geometric structure in other vector bundles. For example, Nanitsini in 2019 used it to construct an Norden structure on the cotangent manifold. The first studies of this vector bundle focused on generalized complex structures by Gualtieri and generalized paracomplex structures by Wade. These 2 structures can be defined as endomorphisms of the sections of this bundle, such that if we square this endomorphism, we get plus or minus identity. These structures are also asked to be integrable with respect to a bracket that can be defined in this bundle, and they are also asked to be compatible with a canonical metric that will be presented later in this talk. However, later studies suggested that this compatibility condition with the canonical metric may be omitted in order to get more examples that can be interesting to study. If we omit this condition, we can see that the definition of a generalized almost complex and a generalized almost paracomplex structure are very similar to the definitions of complex and paracomplex structures defined on a manifold. Therefore, our perspective here is to omit this condition of compatibility with the metric. We will define geometric structures in any vector bundle E, and we will compare the 2 situations when E is the tangent bundle and when E is the big tangent bundle. In the first case, we will obtain the usual structures defined for vector fields. And in the second case, we will obtain generalized structures defined for sections of the big tangent bundle. Okay, so we can take now any vector bundle E over a base manifold M, and in this case, of course, we define a metric as it is usual, a differentiable morphism G that is bilinear, symmetric, and non-degenerate. We know that if the metric is positive definite, we use the Riemannian name, while if it is not positive definite, it will be called pseudo-Riemannian, and the signature of a metric is defined as the number of vectors with positive length and the number of vectors with negative length of a basis of a fiber in the vector bundle. If we change the symmetry condition by an anti-symmetry condition on the definition of a metric, we obtain the definition of a symplectic structure on the vector bundle. Of course, when we work with the tangent bundle, we recover the usual concepts of metrics and almost symplectic structures on a manifold. We know that in order to talk about symplectic structure on a manifold, the omega must be a closed form. When we are using the generalized tangent bundle, we will talk about generalized metrics and generalized symplectic structures. If we take now any symplectic structure on a vector bundle, as it is a non-degenerate structure, we can define isomorphisms between the module of sections of the bundle E and the sections of its dual bundle E star. These isomorphisms will be called musical isomorphisms, and we have 2, the flat isomorphism and the sharp isomorphism associated to omega. In the case of the flat isomorphism, we will take sections of the bundle E to sections of the dual bundle E star using the definition shown in the screen. And the sharp isomorphism will be defined as the inverse isomorphism of the flat isomorphism. This section morphism can also be seen as a bundle morphism over the identity map of the manifold, such that their corresponding diagram must commute. For example, this is the diagram associated to the flat isomorphism of omega, and this diagram must commute. Of course, we can do this. We can define this musical isomorphism for a metric G, and the notation will be the one shown in the slide. Now, I'm going to define the main focus of this talk, the polynomial structures. These structures will be defined as section endomorphism. In this case, I will denote them with the letter J. And they will have a minimal polynomial associated P such that P of J must be equal to 0. We want to focus on two minimal polynomials. The first one is x squared plus 1. In this case, the polynomial structure must be j squared equal to minus the identity map, and we will have an almost complex structure on the vector bundle. When the polynomial is x squared minus 1, we will have that j squared is equal to the identity map, and this structure will be called an almost product structure on the bundle. When the eigenbundles associated to the eigenvalues plus 1 and minus 1 of j have the same dimension, we will use the notation almost paracomplex structure. And in a similar way than the musical isomorphisms, these section endomorphisms can be seen as bundle endomorphisms over the identity map on M, such that this diagram must commute. One important characteristic is that each polynomial structure can induce a dual structure on the dual bundle E star with the same minimal polynomial P, and is defined as it is shown here for each alpha section of E star and for each xi section of E. When we work with the tangent bundle, we will recover the usual concept of almost complex, almost product, and almost paracomplex structures on a manifold. When we work with the big tangent bundle, we will talk about generalized almost complex, generalized almost product, and generalized almost paracomplex structures. It is worth noting that we are not going to focus on the integrability of these structures, so we will always use the adverb almost. To end this introduction, I want to talk about the concept of alpha epsilon metric structures for alpha and epsilon taking the values plus 1 or minus 1. This structure is composed by a polynomial structure J such that J squared is alpha times the identity map, and a metric G that is compatible with the polynomial structure in a way that J is isometric or anti-isometric with respect to the metric G. The value of epsilon will determine if it is isometric or anti-isometric. Depending on the values of alpha and epsilon, we will use different names for these structures. For example, if alpha and epsilon are both equal to plus 1, we will talk about almost product Riemannian structures. In this case, we will require the metric to be Riemannian. And when the structure is almost paracomplex, when J is almost paracomplex, we will say that we're working with an almost paranorthern structure. When alpha is plus 1 and epsilon is minus 1, we will have an almost parahermitian structure. When alpha is minus 1, epsilon plus 1, we will talk about Hermitian structures. In this case, we will force the metric to be Riemannian. And when both alpha and epsilon are equal to minus 1, we will have almost northern structures. Now we are ready to talk about generalized structures or polynomial structures. Generalized structures in the big tangent bundle. We're going to show first 3 canonical structures that can be found without adding more structure on the base manifold M. The first one is, as I said before, the canonical generalized metric G0, such that for each pair of sections of the bundle, say for example x plus xi and y plus zeta, we have the value xi of y plus eta of x divided by 2. This canonical generalized metric is a pseudo-Riemannian metric with neutral signature, And if we change just one sign on the definition of the metric, we obtain a different structure called the canonical generalized symplectic structure. The third canonical structure that I want to introduce is the canonical generalized almost paracomplex structure. In this case, for each section x plus xi, the canonical generalized almost paracomplex structures gives the result minus x plus xi. From now on, I will use this matrix notation that is very intuitive to refer to polynomial structures on the big tangent bundle. It is easy to check that the eigenbundles associated to the eigenvalues +1 and -1 of F0 are respectively the cotangent bundle and the tangent bundle of the base manifold. One property that can be easily checked is that these three canonical structures are related between them with this nice expression. The omega 0 can be obtained using the G0 and the F0. Another property that can be easily checked and that can sound strange is the following: that the generalized tangent bundle is canonically isomorphic to its dual bundle. In this case, we have a lot of isomorphisms, but some canonical isomorphisms are given by the musical isomorphisms of the canonical metric and the canonical symplectic structure. This is something that is very different in comparison to the tangent and the cotangent bundle. We know that both the tangent and the cotangent bundle are isomorphic between them, but we need to define a metric on the base manifold in order to have an isomorphism between these two bundles. In this case, the isomorphism is canonical. Until now, we have talked about structures that arise naturally in the big tangent bundle. However, when the base manifold present more structure, we can induce different generalized structures. For example, the first examples shown are these two generalized almost complex structures. The first one is induced by an almost complex manifold, and the second one is induced by an almost symplectic manifold. Using the matrix notation, the first one takes each section x plus xc to the section jx minus j star xc. And the second one takes x plus xc to minus sharp of omega xc plus flat of omega x. The interesting thing about about these two structures is that we can see as the same type of structures, in this case an almost complex structure or an almost symplectic structure on the manifold. We can see them as the same type of generalized structures. They are both generalized almost complex structures on the big tangent bundle. These two examples satisfy the isometry relation with the canonical metric, as I said in the first slides of this talk. However, we said that we were going to omit this compatibility condition with the canonical metric. Therefore, from an almost complex manifold, we can obtain two generalized almost complex structures on the generalized tangent bundle. The only thing that we have to do is to change the sign of G star. We can put here a lambda that can take the value +1 or -1. This structure is generalized almost complex, and the eigenbundles of this structure can be seen as Witnessiums of the eigenbundles associated to J and J star. Depending on the value of lambda, these expressions will be different. We can do something similar for an almost product manifold. In this case, we can induce two generalized almost product structure depending on the value of lambda, taking values +1 or -1. And analogously, we can obtain the eigenbundles of these generalized almost product structures. They are also given by Witnessiums of the eigenvalues of F and F star. And in this case, we have that for lambda equal to +1, the generalized almost product structure induced will be almost paracomplex if and only if the F structure on the manifold is almost paracomplex. However, for lambda equal to -1, this structure will be always generalized paracomplex, whether F is almost paracomplex or just almost product. If we have a different structure on the base manifold, we can generate different generalized polynomial structures. For example, from a Riemannian or pseudo-Riemannian manifold, we can generate a generalized almost complex structure that is very similar to the definition that we gave before for the one induced by an almost symplectic structure, and a generalized almost paracomplex structure, just changing one sign here. Analogously, if we take an almost symplectic manifold, we can induce the generalized almost symplectic, almost complex structure that we showed before, and a generalized almost paracomplex structure that is very similar to the one induced by a metric, just changing the sign. Now we want to check what structures can be induced if we have in the base manifold a polynomial structure and a metric that are compatible. That is, we have an alpha epsilon metric manifold. Nanitsini showed that when we have an almost northern manifold, we can, that is, we're taking the values alpha and epsilon equal both to -1, we can induce a generalized almost complex structure in the big tangent bundle. We want to propose a similar structure, similar almost complex structure for other alpha epsilon metric manifolds. We are going to take first the values for, we are going to take the manifolds for alpha equal to -1. And in this proposition, we show that when we have an alpha epsilon metric manifold with alpha equal to -1, we can induce these two generalized almost complex structures. They are both, in our matrix notation, they are both triangular. In this case, we use the flat isomorphism, and in this case, we use the sharp isomorphism. Of course, we take the epsilon value corresponding for the alpha epsilon metric manifold. This can also be done for an alpha epsilon metric manifold with alpha equal to +1. Idan Manea showed proved that when we have an almost parahermitian manifold with F being almost paracomplex, this structure is generalized almost paracomplex. And if we do a similar proposition that the one that we have before for an alpha epsilon metric manifold with alpha equal to +1, we can induce two generalized almost product structures. In this case, they are also triangular. The first one uses the flat isomorphism, and the second one uses the sharp isomorphism of the metric. The epsilon value is the corresponding to the alpha metric manifold. And in this case, we have that these two structures will be generalized almost paracomplex if and only if the F structure on the manifold is almost paracomplex. And now to end the talk, I want to present more complicated generalized structures. If we have an alpha epsilon metric manifold with alpha equal to -1, now we have induced two generalized almost product structures, the one induced by the metric and the one that can be induced with this omega structure that is obtained using G and J. We want to induce now a generalized almost product structures that in the matrix notation has the J directly in its description. In this way, we have that this proposition, if we have alpha epsilon metric manifold with alpha equal to 1, we can induce the following generalized almost product structure, of course, for the corresponding value of epsilon. We have here two square roots of 2, and this is a more complicated structures than the ones that we have seen before. Of course, and as we have done before, we can obtain a similar results for the case of alpha equal to +1. Now we want to obtain a new generalized almost complex, not manifold, structure using F, the structure F on the manifold. We have this proposition. This generalized structure is almost complex. We have in the principal diagonal the structures F and minus epsilon F star. and here we have the square root of 2 and the two musical isomorphisms of the metric. So that is all I wanted to talk about. I have here some bibliography that we have used to do the talk from the classical works of Hitchin and Gualtieri and Wade analyzing this vector bundle to more modern works like the one by Nannicini, Weissman, Fernandez-Kulma, Godoy-Salvay, and Ideimanea. And that is all I wanted to talk about. Thank you very much, and I will gladly answer every question that you may have.
Okay, we thank you, Professor Gomez Nicolas, for his valuable talk. If there is any question or comment, please use the question and answer button. Let me check. I think there seems no question or comment. So we thank again to Professor Gomez Nicolas.
Thank you.
Please stop your screen sharing, please.